Does that work? Looks like it's working. So any issues that we need to go over for homework? We're happy with homework? You want to just do a quiz? Let's do a quiz, then we'll do some fields, and then we'll call it a day. So this will be fun. Hopefully this thing works. We're going to find out. I made the mistake of changing the function slightly this morning when before coming to class. Is this a top hat? That's a button. A button? That's a little top hat. They do that. Why? Microcontroller. You making a button for the microcontroller? I should take that. It sounds like okay. Let's see. Get this going. set up here. Oh, I'll simplify it up on the screen. Oh yeah, almost no one simplified. Yeah, see? Okay, fun. Okay. Now you're going to simplify it. You don't have to simplify it because no one else will have it. All right. That looks good. Nice work. All right. Oh, I see. You're just kidding. That's fine. We'll leave it at that. Let me staple this together. Okay, so let's see what we got here. So a little bit minor algebra issues from some of you, but hopefully you were able to set this up. Here's the setup, is that you're going to do replace the y with y and replace the dx with the derivative of x, which happens to be 1 times dt. So I think all of you had something like that as your starting point, and then the algebra, maybe we need to review maybe we need to go back to algebra 1/2. Pre-algebra, actually. So e to the t to the fourth is e to the 4t. So that simplifies to this. Then you can do your antiderivative of e to the 4t. If you need to, you can use substitution, but I didn't. I just know that the integral of e to the 4t is e to the 4t over 4. So I just have this extra 16 over here, or extra 4 in the denominator. And then I just have to evaluate this from 0 to natural log of 3. And so we have this. Don't forget the fact that e to the 0 is 1. So I've got this. And so, yeah, this is where I was like, come on, can't you just type it into your calculator at least? But anyway, when you do, if you do the simplification, this joyous thing happens and you get the number 5. I was trying to give you a subliminal message that when you do your end of course surveys, there's your answer. But anyway, maybe I made it too hard as a result, but there it is. Okay, so let's switch over to, where is it, PowerPoint land? There it is, to this. So we're just going to do a couple of problems to show you how to do work through a vector field. So this is one of the big applications of this. And then hopefully we'll get to conservative vector fields as well. If we don't do that today, we'll do it on Monday after break. But for sure, we'll do several of these. And at least I'll hint at the conservative vector fields. So let's take a look at this one. The big issue here with problems like this is setting up your curve. So we have this counterclockwise direction, semicircle, centered at the origin, radius 1 above the x-axis. Okay, so let's set this thing up, see if I can draw this relatively well. So I have a semicircle, counterclockwise, radius 1 above the x-axis. I think this is what I'm going to have. From 1, 0, over to negative 1, 0. Whoops. Yeah, good enough. So this is a circle. Hopefully this isn't going to throw you too much, that you can actually parameterize this relatively easily, just saying x is equal to the cosine of t and y is equal to the sine of t. So you remember that I gave you this sort of cheat sheet on how to parameterize straight lines. So a straight line is pretty easy to parameterize. Now circles are also relatively easy. Just use cosines and sines, and don't forget that x is r cosine theta, y is r sine theta. So you could probably do a pretty good job there. Now, to remind you how you do this, we're going to be computing this, the integral of f dotted with dr. So I always think in terms of force through a distance. So F dotted with dr, F is the force, which is represented by the vector field, and dr is the distance, represented by this right here. So what we're going to want to do is we're going to want to write down, first of all, our curve. Then I'm going to do the derivative of that, and I'm also going to write down the function, and then I'll do the dot product. So I always try to lay it out nicely like this. I'll explain in just a minute, but I think we can all do the derivative. So go ahead and do your derivatives, which I know is super basic, but give me a chance to find someone. Sarah, you know the derivative of r here, don't you? Nice. Okay, so there's dr. I need to find f. Where is f? Oh, there it is up there. But notice that we want to have f not in terms of x and y, but in terms of t. So down here, what I'm going to do is I'm going to take this f, and I'm going to replace the x's and the y's with whatever the curve I'm on looks like. So in this case, f is equal to, let's see, negative sine of t times I. Oh, interesting. So just so you know where that came from up here, replacing the y and the x with the appropriate stuff. So it is exactly the same as dr in this case. It's not always though. Now let's do the dot product of those two things. I know you can do the dot product, so go ahead and do it, and then I'll find a volunteer to do it. Rostin, do you think you can do the dot product of these two things?
Sure.
Let's hear it.
We have sine squared of t I plus cosine squared of t j.
All right, I'll take all of that except for the I and the j, because we're doing a dot product. You get rid of the I and the j. So dot product you take, just to remind you, this is why I like to line these up like this. You take the product of the x term or the I term, and then add that to the product of the j term. And if we had a k, if this was in a vector function through 3 space, then you'd have a k as well. And you just do that, just add them up. So yeah, you end up with a nice scalar, no I, no j, no k. Now that we've got all that, let's set up the integral, and hopefully you can see what joy we're going to have doing this. Let's see, we're going from, I never actually specified. Here t is equal to 0, and over here t is equal to pi, right? We're going from 0 to pi for this particular vector function. So 0 to pi, sine squared plus cosine squared. Oh, look at this. What's going to happen here? What can we do? Yeah, it's equal to 1. So this, one of our favorite, I don't know about you, but I remember learning about trigonometry, suffering through all of those identities. But when I got to this identity, this gave me a great amount of joy, because you take sines and cosines, these things that cause so much grief, and it combines and becomes just 1. All right, now I can do this antiderivative. Zechariah, what is the antiderivative of 1? T. Yeah, it's just t, isn't it? So t goes from 0 to pi, and that's just going to be pi. So the amount of work done by this vector field, I'm not sure what the units are in this case, because I don't know what the underlying units are, but it's pi. Pi is the amount of work done. So apparently what's happening, remember that when work is positive, it means that the vector field is helping you out, if you want to think of it as riding your bicycle through wind. So the vector field is helping you out here. If it's a magnetic field or a gravity field or whatever it is, whatever's happening along this path, you're being helped by the vector field. And here's how much you're helped, pi. If this was a negative number, it would mean you're going against the wind. You're being hindered. Okay, let's do the same thing, but now we have a line segment. This is exactly the same problem. So I want the work done by this vector field, but now I'm going to go with a line segment. So let me just sketch the situation. And here, I'm starting here, 1, 0, ending over here, -1, whoops, 0. Get rid of that superfluous negative. And we're going straight along that axis. So this is slightly different. Notice back here, you were going along a curve. It's the same vector field. Now we're going along this straight line. And I want to know how much work is going to be done by the vector field in this case. So I guess I need to parameterize my straight line. I don't know if you remember the sort of cheater way of doing this. I'm sure Cooper would, but he's not here. Avin, do you remember how to write the parametric form of this line? Well, what's the starting point for the line? What's that? 1, 0. Yeah, 1, 0. So I'm going to put that down to begin with. And then how far have you gone? So -2 times t. And how far have you gone in the y direction? Yeah, 0t. So that's all you got to do is put your starting point down, and then how far have you gone times t, and then you're all set. So this one's pretty straightforward. You have 1 minus 2t for x, and then just 0 for y. Okay, so here is my vector function, 1 minus 2t plus 0j. I need dr and I need f in terms of t. So let's do dr. Lucas, what's the derivative of r? Yeah, just -2i. I'm going to put the 0j there just as a placeholder so that we remember about it, but it is 0. And then Rayland, what's the function, the actual vector field in terms of t? Because I have it in terms of x and y up there. All right, very nice. Okay, so far so good? Yeah, if anyone has any issues, let's deal with it now. Now we need to do the dot product of these two things. And let me just put up this sort of remind you how to do dot product. I'm going to put those two together and these two together. There we go. So let's see who gets to do this. Cheyenne, what's the dot product of these two things? Oh, just 0? Yeah, I guess it is. You have 0 for those yellow things, and then the green things add up, it's just 0. So if I wanted to set up this line integral, it's going to look like this. We're going from 0 to 1. Because of the way that this got parameterized, you're going to just 0 to 1 will be the limits. The function is 0 dt. And this actually might be so simple that it's hard. Let's find out. Sam, do you know what the integral from 0 to 1 of 0 is? Do you know the antiderivative of 0? It's, well, like a constant. Okay, I'll give you the 1 or the constant. And then, so here, we'll give you a constant there. And then you're going to evaluate a constant from 0 to 1, which is going to be that constant minus the constant, which is 0. Yeah, so it's just 0. Yeah, like I said, it's so easy. It's hard in this case. So anyway, Yeah, so the work done is 0. So interestingly, if you go from the point 1, 0 to negative 1, 0 along this path, the work done by the vector field is 0. If you go along this path, the work done by the vector field is pi. Now, did I do one more? No. Yeah, I guess this getting a little tedious here. Just a minute. What I wanted to show you, here we go. Let's get rid of, can I get rid of the ink? Hopefully clear. Yes. Okay. So you might wonder, what does this vector field look like? Well, it's this one over here. So this is the actual vector field for those two problems. And so let me just show you on the vector field what's going on from here to here. There we go. So there is the straight line. And then this here is the semicircle. Now, we won't do this one, but you could imagine this semicircle down here. Wouldn't be too bad. It wouldn't be too hard to parameterize that. But you can see that going through the middle, you have 0 work done by the vector field. If you go up around this way, that actually you get a boost from the vector field. What about going down this way? Can you see what's going to happen if you go that way through the vector field? I'm sure Haven would know, but he's not here to tell. But does anyone want to volunteer what's going to happen if you go down here?
Negative work.
Yeah, it'll be negative work. So you'll actually be hindered by you're trying to bike into the wind here. So you're like, oh, it's harder. So you're actually being pushed against your, it's harder to go that way. So this is a situation with this vector field that is not true for all vector fields. So this is a special situation. Let's see, that vector field. Yeah, so this is a little bit harder to, let me see if I have this. And here, do I have this? Line segment. No, that one's boring. So no, let me just, let's do this one here. So this one is different. So let's do the same thing with this vector field. So we're going to go from here to here. And we're going to do it in 3 different ways. We'll do this semicircle. And we've already parameterized this, so we aren't going to belabor this too much. And you might say, well, what is that? We're going to do that semicircle. And then we're going to also do, well, maybe. We'll see if we get sick of this. Do that semicircle. Okay, so I need to tell you what that vector field is. So this vector field is the field I minus j. That's it. I minus j. Okay, so let's give this a go and see if we can do this. I'm going to have to find a nice blank page. Here's a nice blank page. So give me a sec here. I'll write this down. Our vector field is I minus j. I know you're saying, where's the x and the y? Well, this is a constant vector field. This is one of the easier ones. And we're going to use, first of all, this. So we're going to go along this particular route. So that one we can compare is the one that goes up and over the blue curve. So we'll do that one first. Then we'll do the red one, and then if we need to, we'll do the green one. But these are pretty easy because of the fact that this is a constant vector field. So we need r prime, dr. We'll only do this. Oh, actually, we did this already, didn't we? We know what dr is. It's going to be negative sine ti plus cosine of tj. F is already written without x's and y's. So I'm just going to write it like this. I minus j. I'll put a 1 in here just as a placeholder. And then we're going to do f dotted with dr. All right, like I said, I know everyone can do this, but let's just make sure. Sam, what do you think? What's f dotted with dr? All right, very nice. So what we need to do now is we need to integrate from 0 to pi of f dotted with dr. So negative sine of t minus cosine of t dt. So there's step 1. I'll put step 2 over here because it won't take as much effort or space. So give me a sec here while you're doing your calculations. Okay, let's see how we did. We need an antiderivative. I know that person could do it, but she's not here. But Zechariah is here. What's the antiderivative of this black integral over this integrand right there?
Cosine of t minus sine of t.
All right, very nice. Cosine of t minus sine of t evaluated from 0 to pi. All right, very nice. Evan, did you get that? And did you plug in the pi and the 0? What'd you get? -2 is the final answer. So you're working, it makes sense. I mean, the way I drew this, you can see that I'm going against the wind predominantly. I mean, there may be a little bit here at the end where I'm going with the wind, but I'm going against the wind. Here the wind is oblique to your, perpendicular to your motion. Maybe at the very end you might get a little bit of a boost from the wind, but there it is. Okay, so let's do this other one. There we go. So I did most of the work for you because it's all super basic. The vector field is still the same. The vector function, which represents the curve, is going to be the same thing. This is that line that we had from from 1, 0 to -1, 0. Derivative is still the same as before. I did the dot product for you. I just got negative because it's -2 times 1 plus 0 times -1. Yeah, -1. So all you have to do is the final step. It's not bad. Doing the integral of -2 dt. Rostin, do you know the antiderivative of -2? Yeah, -2t. And then we can plug in these two things, and you just get -2. Look at that. We got -2 from both of those. And actually, you could, let's see, where's that thing again? There it is. So the green one, let me just mention the green one so that you know that you could do this if you wanted to. The green curve is going to be, you could do this a variety of ways. Maybe we should just stick with what we know. Cosine of t I plus sine of tj. Same curve as with it's the same circle, but in this case, you're going to have t go from 0 to -pi. So you're going down around. So you could do this. It's going to look very, very similar. But if you did the integral of f dotted with dr, you actually get -2 as well. So this vector field is special. It's a vector field where it doesn't matter. It turns out that it doesn't matter what path you take between these 2 points. So if you start over on the right and end over on the left, it doesn't matter what path you take. You could go some crazy path through this vector field. And if I did the integral of f dotted with dr for that curlicue path, I would get -2 as well. So it's just an interesting fact about that vector field. It's not true of these other two vector fields. These two vector fields, you don't have that. You can see here clearly positive, this one's 0, this one's going to be negative. You get different answers depending on what direction you go. The same is true for this vector field in the middle. If we went from 1 to negative, there it is, from there to there, if we went straight along this path, wait a minute, I may have to recant. This one, I think, is going to be the same because you get 0 if you go that way. If you go this way, you get 0. Yeah, I think this one is going to be 0 all the way around. Interesting. Okay, so this one's the only one that's special. The one in the middle is similar to the one on the left. We won't actually do it. I could, because that one I could write down. That one, the vector field, I think, is just x times I plus y times j. So x times I plus y times j. So you could actually do the same thing with this one in the middle, and you would find that all of your, no matter which way you went, you could go some crazy curlicue way. As long as you start and end there, you end up with the same integral. So we have a special name for vector fields that are like this. So these two are special. That one is not. So these two vector fields, we call them conservative. And this isn't a political statement. It's conserving something. Now, you know about conserving stuff, don't you? You've learned in your science classes, conservation of, fill in the blank. I'll bet you if we Googled this, I'm curious to see what the autocomplete is. Just a minute. I'm going to pull up Chrome here. Let's see. Conservation of. Okay, so the first one is momentum. Conservation of energy, conservation of mass, conservation of matter. So there's all sorts of conservation, things that you know are conservative. They are conserved. So gravity is a conservative vector field. A magnetic field is conservative. And we'll talk about what makes them conservative later on. But the important thing about conservative vector fields is once you know a vector field is conservative, it doesn't matter how you get from point A to point B. The integral will be the same. And not only will it be the same, but on Monday we will have what's called the fundamental theorem of calculus for vector fields, in which you learn that there's a super easy way to compute that integral, that line integral. All right, let me double check your homework so that we know that it's not going to blow your mind. And then look at this, we can even end a few minutes early. Let's see, this is the homework that was due today, supposedly. Let's get rid of that. And then let's do this just a minute. This is the homework that's due next time. So let's see. So you have a three-dimensional vector field here. Line integral through that vector field. It's the same exact formula. So the ones we did today were actually quite simple. You can see this is a little bit more complicated, but you're going to get a polynomial here. It's not going to have no cosines and sines. So that one's not too bad there. Let's just double check. Here we are. This one looks okay. Here you have sines and cosines, but we've already done a few of those. We can hope that they'll cancel. Actually, this one isn't going to be quite as nice. That one I did earlier. Oh no, that one I did earlier. Not with you. I was just double checking something. And then this one, yeah, three-dimensional. But it'll be exactly the same. Just make sure you do f of r, and then do r prime, and then do the dot product, and then the rest of it is just, this one will be a polynomial when you get done. All right, so I think that's it, other than to just remind you to do your end-of-course surveys, and if you're having trouble choosing what you're going to answer your question, you can always just use this as your answer. I joke. It really, do it honestly. But please do those. I'll be able to figure out how many. I won't know who, but I'll know how many of you have done them, and I'll let you know on Monday. And maybe if everyone does them, I'll have something special when we have our little brunch, Christmas brunch on the 6th. So, all right, well, thanks for coming today. I appreciate it. I'm going to stop the recording in case you want to come and complain to me about anything. Stop it.